All right, so now that we've talked about acids and bases and pH, we can talk about indicators. So what we use to visibly see the pH based on colors. So an acid-base indicator is a substance that changes color when the pH of a solution changes. Indicators exist in two forms that each have a different color. Acid-base indicators have really complicated molecular structures and formulas. Therefore, we use abbreviations to identify each of the indicators. So typically, what we're looking at is HIN will be the lower pH form of the indicator. Note that it has an H, meaning it's kind of acidic, and low pHs mean they're acidic. Therefore, this is more acidic. Sorry guys, I forgot my stylus today, so I'm just writing with my finger. It's not going to look great. IN minus, so whatever else is left, is the higher pH form of the indicator, or more basic form. All right, so if you see here, this is phenolphthalein structure. All right, it's really, really complex. So what we would call phenolphthalein is HPH when I'm writing it on paper. That would be the abbreviation. You can find all of the abbreviations on the back of your periodic table. Okay, so each indicator has a pH range that is unique to its particular substance. So again, see the back of your periodic table. What we're going to do is we are going to look for litmus. It's not actually on the back of your periodic table, so we'll just talk about it quickly here. All right, so litmus's abbreviation will be HLT. So its pH range is from 4.5 to 8.3. All right, so when something is acidic, what we see is the lower pH range. Okay, so what we would see is something where if it is HIN, it's acidic, it's less than 4.5, we know that acidic things are red. Okay, when it's IN minus, so just LT minus, litmus, we see that it would be blue, so slightly basic. Bromothymol blue is on the back of your periodic table, so we're back to that. If you find it, its abbreviation is HBB or BB minus. Okay, its pH range is 6 to 7.6. When it is in its acidic form, or the pH is 6 or less, we see that bromothymol blue would be yellow. It's the first listed in that range. When it's blue, we know that it's greater than 7.6. In between those two, so if it's between 6 and 7.6, like 6.8, we know that it would be green. Okay, color wheels coming into effect here. Phenolphthalein is HPH. Its pH range is 8.2 to 10. It's colorless when it's less than 8, and it goes pink, very bright pink after 10. So again, the range goes from 8.2 to 10, and the color corresponds directly with that. Fun facts. The indicator litmus is actually obtained by lichen. So litmus paper is prepared by soaking the paper with the solution of lichen and then drying it. So natural color changers. Okay. How are we going to use these? To mark the end of a titration analysis, which we talk about next chapter, so no worries, or to estimate the pH of a solution. So it can replace the work of a pH meter. It's not as accurate, can't give an exact number, but it can give a good close range. So predict the indicator color for the specific pH. If bromocressyl green has a pH of 2.8, we want to look at our table, and we can see that bromocressyl green changes color between 3.8 and 5.4. So because 2.8 is less than 3.8, we know that it's going to be yellow. Oops. Right? If phenol red has a pH of 8.5, we know that it's greater than that top end of the range of 8, so it must be red. If cressyl red has a pH of 8, cressyl red has two ranges. So Crescel Red has a change between 0 and 1, and then again between 7 and 8. So because 8 is between 7 and 8.8, we know that it's in the midpoint. The midpoint of yellow and red would be orange. Crescel Red at 1.6 is between those two ranges, and so we know that it's going to be yellow. And Methyl Violet at 1 is going to be between yellow and blue, therefore it's going to be green. All right, the other example is when we get these ranges, we can estimate the pH of a solution. So the solution was tested with several indicators to determine the pH. The following results were obtained. What is the pH of the solution? So what I suggest is what we're going to do is we're going to draw a number line representing pH, and from each of these pieces of information, we're going to add to our number line. So an orange 4 is yellow. Orange 4 has a color change between 1.4 and 2.8. Anything beyond 2.8 is going to be yellow. So at 2.8 and beyond, it goes to yellow. All right, so what we're going to do is we're going to draw 2.8 in on our line here. 2.8, and we know that this has to be anywhere beyond 2.8. So anywhere along here, the pH can be. Okay, so at 14, it would still be yellow. So that doesn't narrow it down very well. What we're going to do then is look at the next piece. So bromocresol green. Bromocresol green is blue at 5.4 and greater. So at our number line at 5.4, we know that at 5.4 or anything above 5.4, we're going to have bromocresol green being blue. So now it can't actually exist between these two, otherwise bromocresol green would be the wrong color. So continuing on, we're narrowing ourselves down here. Phenol red being yellow. Phenol red turns yellow at 6.6 or less. So we'll write that on our number line. So 6.6 or less. Now we know that it must be within this for all three colors to be the right color, or all three indicators, sorry, to be the right color. Last one, bromothiamyl blue being yellow. Bromothiamyl blue is yellow at 6 or less. All right. So now we've narrowed ourselves down to this area right here. So the pH is less than or equal to 6.0, but greater than or equal to 5.4. So we've created a range for the pHs. This is what you want to get to. All right, your homework for this is the Acid-Base Indicators worksheet on Moodle. Make sure you take a look at that.